Okay, and start our presentation. Okay, good morning, everyone. I've got quite a presentation for you today, as you may have flipped through the slides. Some of them are quite intimidating. I understand, I agree. But fear not, we'll go through some of those intimidating slides, hopefully slowly, one piece at a time, and see if they make sense. We are going to be doing some pretty heavy lifting with the algebra of trying to make the points that I would like to make this morning about using algebra as a language. So I've chosen three topics. I don't know if we'll even get to all three. We'll see how much time we have. But I chose three topics from the real world. One being the law of buoyancy, centering around the famous story of Archimedes and the crown, and his crying of Eureka, getting into the bathtub. The second is looking at the speed of waves, different kinds of waves, and what we can discern with a mathematical analysis if we have two different waves coming at us at different speeds. By looking at their time delay of how they arrive, we can measure the distance that those waves, if they're coming from the same place, if those the distance that those waves are coming from. For example, an earthquake creating two different kinds of waves. And the third look at a little bit in the world of chemistry to balance equations, balance chemical reactions, and it's a nice little application of simultaneous equations. The balanced equation creates a series of equations which you're trying to make all true at the same time. And by solving those properly with one coherent solution, you in fact wind up having the right numbers in front of the different compounds to have the reaction balanced. So those are the three that I would like to look at as just different kinds of examples of where algebra can be used in the real world. Of course, there are millions. One could pick other things, but I thought these could serve our purpose. So let's get started with the first one, looking at the force of buoyancy. I remind you that if you have an object which is stable in equilibrium, then that must mean that the forces on it are balanced. For example, the book on the table has two forces on it. One is the force of the earth pulling it down, better known as gravity, better known even than that, than the weight, which represents the force being pulled down. And of course, the reaction force of the table pushing up. Reaction force comes from Newton's words, using in his third law that for every action there is a reaction. So from that phrase of long ago, that it's still called that in the world of physics as a reaction force, reacting to an equal reaction to the force of gravity. So this is what creates an equilibrium in a body. And it doesn't change, the fundamental physics doesn't change if you have something, for example, floating in water. If it's an equilibrium, just as the book on the table, one would expect that the forces on the object floating in the water would be equal. There would be an equal and opposite set of forces. Well, the weight doesn't change. The object still has weight. The earth is still pulling it down, but now it's floating in the water, so the water is holding it up. But that's a little strange because it holds up some things and not others. So it's not like the table in that sense. There's something else going on, and that force is called the buoyancy force. And the thing we notice about the buoyancy force, very interestingly, which is what we want to get to, is that sometimes for some objects need to sink lower in the water before the buoyancy force can actually give the object the condition of equilibrium. That somehow or other the buoyancy force is dependent upon how low the object sinks in the water. So we have three examples here of a light cork ball, all the same size. These balls all have the same volume. They have all the same radius. And so for cork ball, it doesn't have to sink very much at all in order for the buoyancy force, wherever that comes from, to equal the weight, so we have an equilibrium situation, just like the book on the desk. For wood, we noticed that the wood ball has to sink lower in order to have the buoyancy force, again, equal to the weight. Notice the arrows. For the cork, there's just one arrow up and down. For the wood, which is heavier, we have a heavier 2 arrows for the weight, so we need 2 arrows representing the buoyancy force. And finally, for an iron ball, the buoyancy force doesn't seem to be doing the job. The buoyancy force, in fact, the iron ball is sitting down at the bottom of the jar. So the weight here is greater than the buoyancy force, but the object still is in equilibrium. And the reason here is that it's really not showing the fourth force, which is the force of the bottom of the jar, doing exactly the same work that the desk is doing in our first example. With those 4 forces, we have reached equilibrium, and the buoyancy force plus the force of the bottom of the jar does in fact equal the weight, and we have our iron ball again in equilibrium. So the buoyancy force always exists, even when it's not doing the total job of having something floating. The buoyancy force is there. It just, with the complete submersion, the buoyancy force clearly in that case is just not great enough to overcome the weight. So it sinks to the bottom, and sure enough, then the bottom of the jar will supply the rest of the force. So I ask a question that we'll see if we can't analyze. What percentage of the volume of a floating object is submerged under the water? What percentage of the volume? Notice the cork has a smaller percentage submerged than the wood. And in fact, the iron ball has 100% of its volume submerged under the water. What determines this? That's the question we'd like to analyze here using our algebra. And of course, the person who discovered the fundamental law of physics, which will answer this question, is Archimedes with his law of buoyancy. And the law of buoyancy is this: the force of buoyancy on an object equals the weight of the water displaced by the object. It's kind of a mouthful, read that again. The force of buoyancy is equal to the weight of the object, the weight of the water pushed away by the object. How much water is pushed away is exactly what the buoyancy force is. So if you can push away enough water so that that weight is equal to the weight of the object, it will float, because we will have then the buoyancy force equal to the weight of the object, and we will have reached equilibrium. So it's the weight of the water displaced. And this is why the amount of the volume submerged in the water is so important, right? Because the more of the object is submerged in the water, the more water is being displaced, and the greater the buoyancy force. Okay, so that's the intuitive idea. And I purposely picked something which I thought would have an intuitive appeal, so that the algebra is not going to uncover any great discoveries for us here, but they will confirm and reaffirm our fundamental intuitive understanding. My point here in this exercise is to see how the algebra can reinforce what we already know in terms of in terms of this whole process of buoyancy. We'll look at another situation after this in which we maybe can derive new knowledge, but here we want to confirm intuitively what we know. So we have a buoyancy theorem. We want to prove something. We want to prove that an object floats only when its density is less than or equal to the density of water. Now, again, this may be intuitively obvious to you, having a feeling of density. We think of the density of an aluminum ball compared to the density of an iron ball, cork ball. And yeah, somehow or other, it's the density which is determining whether it'll float or not. Well, let's see if the mathematics can actually show this to be so. We can actually prove this statement as a theorem mathematically. That'll be our initial goal. So we have to start by, of course, defining density. I'm going to define density. I'm going to use the word density is really the weight density. It's really, we're going to be talking about weight over volume. As many of you know, the real formula, the real definition of density is mass over volume, but we aren't here yet. We don't need mass. We just need the more simple idea of weight. So I'll be using the word density, but technically what we're talking about is weight density as opposed to the real density, which is mass over volume. We'll be talking about weight over volume. And let little d be the density of water, which is basically 1 in the metric system. It's 1 kilogram per liter. It's it's 1,000 kilograms per cubic meter. It's 1 gram per cubic centimeter. In the metric system, it's basically 1. So that's be an easier number to work with, because the density of water will be a great factor here when we want to calculate the weight of the water displaced. It is the density of water that will be able to tell us what that weight is, what that buoyancy force actually is. So here's our proof. Let us assume that we have an object of weight W and volume V, and it floats. Okay. And let V sub S be the volume of the object that is submerged under the water. That's what we're looking for. How much of the volume is under the water? We'll call that V sub S. V sub S, of course, is a piece of V. Okay? It's the part that's under the water. So by definition, V sub S must be less than or equal to V, the entire volume. For the iron ball, V sub S is equal to V. For the cork ball, V sub S may be, I don't know, 1/3 of V, 1/5 of V, something like that. But the volume under the water is a percentage of the total volume. So we've defined our terms. And now the density, we can compute. The density is the weight over the volume. That's its definition. And the buoyancy force is equal to the weight. Why? Because it floats. If we assume that this thing is floating, then it's in equilibrium, and therefore the buoyancy force equals the weight, and we have a floating object. Okay, so we have a couple of equations. Now let's use the law of buoyancy and the definition of density. The buoyancy is equal to the weight of the water displaced. That's Archimedes' principle. And what is the weight of the water displaced? Here's our first application of these ideas. It's equal to the density of water times V sub S. Let's think about that. That needs to make sense to us. First of all, notice that the buoyancy force is a force. It's an equivalent to a weight. And yes, density times volume is a weight. You look at your basic formula up above, right above it. Density is equal to weight over volume. If you solve for the weight, it's equal to density times volume. So a density times a volume is in fact a weight, given the definition of density. And what is that weight? What is that buoyancy force? What is the weight of the water displaced? Well, it's the density of water times the amount of water displaced. But the amount of water displaced is exactly V sub S. Right? The amount of water displaced is exactly how much of the ball is under the water. So this is the buoyancy force, little d times V sub S. And of course, the weight, just solving the density formula for weight, bringing the volume up, the weight is equal to density times volume. So I ask you to hold that thought among many in your mind, that weight is density times volume, just another way of writing the density formula. Well, we're told that these two things are the same, right? Since it floats, we're told that the buoyancy force is equal to the weight of the object. And I certainly can take that equation and solve for big D over little d. Okay, I can bring the little d underneath the big D on one side of the equation, and therefore bring the whole volume under the volume submerged under the other. Basically, I'm reversing and cross multiplying. That's all I'm doing. And I get that the density of the object over the density of water is equal to the volume submerged over the total volume, which of course is less than 1 by definition. Right? V sub S over V is less than 1. And so forth. Yes, we have proved our theorem. that the density of the object is less than or equal to the density of water. Okay? Certainly, I have a numerator over a denominator is less than 1. That means the numerator must be smaller than the denominator. So I proved my theorem. This is something I think that intuitively we do know, but it's interesting to see how the algebra working from Archimedes' principle, working from the law, we can make this deduction that if something floats, its density is less than the density of water. And this, of course, is why a great iron ship can float, right? Because of the surface of the shape of the hull. When you put the great ship into water, it pushes away so much water. It actually pushes away its own weight in water without sinking, okay? Because the overall density of the ship, as heavy as it is actually less than the density of water. So mathematics can, in a sense, give us new knowledge, although it may be intuitively true to us. It certainly has proven something. But there's we can take something from this equation that we've derived here. Take a look at our equation from the top there, this one here, therefore, okay, that d, little d times v sub s is equal to d over v. I can solve for v sub s here. V sub s is equal to the ratio of the densities times the total volume. Look at that, guys. That's a percentage of the volume. The volume of underwater is a very definite, specific mathematical percentage of the total volume. What percentage? Big D over little d. Now, remember, big D is actually a number smaller than little d. So it is a fraction. It's a fraction of the volume, the total volume, the volume underwater. Well, that's not surprising. But what is nice is that if we know what these densities are, we can answer a very, very simple and curious question. What percentage of the volume of an iceberg, for example, is submerged underwater? We all know this from the Titanic story, that it's a much greater, the greatest percentage of an iceberg is underwater compared to what you can see on the surface. We know that the iceberg underneath is the great bulk of the iceberg. Well, just how much it is? Well, let's apply our formula. The density of ice is less than the density of water. That's why it floats. The density of ice is 0.92, as opposed to the density of water is 1. And so applying our formula, the volume of the iceberg submerged is the density of the iceberg over the density of water times the volume of the iceberg. 0.92 over 1 is 0.92. So 92% of the iceberg is actually underwater. And notice our formula does not care about what V is. We had to make no specific assumptions about V. This is true for any object of a mass of W, a weight of W, and a volume of V. The mathematics does not care about the particular details. It only cares about, the physical laws, relationships involved. So the volume of an iceberg is 92% always under the water and therefore 8% above the water. Well, I have a couple of cute pictures I picked. Here's a real iceberg here. And here's some ice in some jars, okay, with a little bear and a couple of penguins up on top. And it looks about right that we've got about 8% of the volume above the water and below. And I found this very interesting article in Quant magazine. See if we can get out here. We hold our breath with my bandwidth. Okay, we got out there. There is some ice floating in a glass, and this is about proving something about the ice. But if you will start this thing, here's a big mass of ice, and I ask you to look at the ice up on top. As the, let's see, have I cut off the, yeah, better. Okay, as the ice cube melts, notice that the amount of ice above the water stays in proportion to the amount of ice below. It's always about 8% of the total ice altogether. So what's happening here is the ice cube in the water is melting. the ice up on top and the air is not. It's what's going on under the water, which is melting the ice. But as the ice melts in the water, that ratio of 8% to 92% remains. So as the ice disappears under the water, the ice above the water also disappears in that same percentage, always remaining 8% of whatever ice is left. Okay, I will take my life and I hope I got that out. Let me close that down. Okay. So before we go on to the story of Archimedes and the crown, do we have any questions? No questions. Okay.
Nothing in the chat.
Okay, thank you. So let's apply this idea. Archimedes applied this idea with the famous story of the crown, which apparently is something that really did happen. Archimedes was a very good friend of the king of Sicily at the time, and the king. The story goes, the king was given a crown, a gold leaf crown, very complex object, complex volume. No easy way to measure the volume. And as he held the gold crown, he was told by the goldsmith, who said, "Sire, this is a crown of pure gold." As he held it, he just had the feeling it seemed a little light to him. So he went to Archimedes, says, "Archimedes, I want you to look into this to me. I don't know about this crown." He says it's pure gold. Go ahead and look into this and let me know if, in fact, that can be substantiated or not. And that is the basis of the story. And probably the most famous incident coming out of the whole story, maybe the most famous thing known about Archimedes, which is ridiculous because he is one of the greatest mathematicians of all time, and his work has such a powerful and important influence on all of mathematics after his time. But the most famous thing we know about Archimedes is when he got into the bath and the water rose as he got into the bath. He had this great realization, which we'll talk about in a minute. And ran out of the bath, down the street, yelling, "Eureka, I have found it." Okay, so what is the basic idea? The basic idea is if you put an object into water, right, the water level will go up. And that's what he saw, apparently the water overflowing out of the bath. And one thing that he realized, one Eureka moment, was that he could now measure the volume of the crown by literally doing this, right? Seeing how much the water would rise when the crown was submerged. So that solved one of his problems, a difficult problem, to measure the volume of such a complex object. But historians think that that's not really what got him so excited. What he jumped from there mentally, he realized that having a good number for the volume is what would allow him to actually, move to the solution to the problem, the detailed solution. And that's what got him so excited. And that's what we want to take a look at. So the story goes that what he did was he took a lump of gold, pure gold, that was exactly the same weight as the crown, the complex shape of the crown, but certainly he could measure out an amount of gold that was equal to the crown, and balanced them, made sure that in fact he did have the same amount of gold as he had, oops, sorry, jumped the gun, as gold. So we'll call C the weight of the crown and G the weight of the gold. They are equal. And then he put them in water. And this is what he got. This is what happened to his balance. Well, the weight doesn't change. Just because it's in water doesn't mean that the earth is pulling it down any differently. The weight is still the same, but why does it no longer balance? Well, of course, it's the force of buoyancy. The force of buoyancy on the crown is apparently greater than the force of buoyancy on the gold, and therefore the crown will seem to weigh less because the buoyancy is doing a better job. Now we can stop right there, and intuitively we can think, well, why is the buoyancy force greater on the crown? Because it's pushed more water away. That's Archimedes' principle. Of course, we know that now. Archimedes had to discover this. Again, we'll look through the mathematics of that discovery. But just jumping to the conclusion, the law that if the buoyancy is greater, that means the amount of water pushed away is greater. That means the volume of the crown is greater than that volume of gold. Okay, as difficult as that volume is measured directly, here it's the balance in the water which is doing the job. But if we look at the math, sorry, the gold weighs more than the water. The gold weighs more than the crown in the water because of the buoyancy force. The buoyancy force on the crown is greater. So defining our terms, let's let V sub Z be the volume of the crown. Let's V sub G be the volume of gold. And yes, intuitively to us, we can see because of what we're looking at here in that balance, that the crown is pushing away more water. Therefore, we're going to expect the volume of the crown to be greater. That's what we want to demonstrate. Okay, so the weight of the water displaced, which is the buoyancy force according to Archimedes' principle, is equal to the weight, is greater than the weight of the displaced water of the gold. That's why we have the balance as we see it. Well, what is the buoyancy force? The buoyancy force is the density of water times the volume of the crown. The crown is totally submerged. So it is the weight of the water displaced. The weight of the water displaced is the density of water times the volume that's being displaced, which is the volume of the crown. Again, I ask you to think about that formula again. Density times volume is weight. And there's the weight of the water, which is the buoyancy force. And in the same way, the weight of the crown, just the weight of the water displaced by the crown is the density of water times the volume of the crown. And we know that those have that relationship. We know that big B is greater than little b. Well, if we just cancel out the D's, the density of water on both sides, we do in fact have the volume of the crown is greater than the volume. Yes, intuitively, we understand this. We saw this right away by looking at the picture of the two objects submerged in the water. But here we see the algebra is reinforcing what we know by using the law of buoyancy. And that's the point I'm trying to make, guys, right? That using the laws of nature, using the mathematics, we can draw out this kind of knowledge. Whether it's intuitive or not, is another story. Sometimes the knowledge is intuitively known already, that's fine. But many, many times, of course, we know this is the road to discovery. Okay? This is how we discover things about the world. And finally, the density of the crown. Well, the density of the crown, by definition, is the weight of the crown over the volume of the crown. That's what the density is. And the density of gold, similarly, would be the weight of the gold divided by the volume of the gold. But take a look. The two numerators are the same. We've agreed that C and G are equal. That's what the first picture shows. So if the numerators are the same, and we've established that the volumes are different, right? That the denominator of the D sub C, the density of the crown, if that volume is greater, if that denominator is bigger, then the fraction is smaller. Right? With the same numerator, a bigger fraction gives us a bigger denominator, gives us a smaller fraction. So in fact, the density of the crown is in fact less than the density of gold. Just what the king surmised as he kind of just held it in his hand and looked at it and said, this seems light to me. The density, in fact, was not the same as the density of pure gold. If you want to look at it purely algebraically, setting those two numerators equal to each other, solving for what the numerators are, the density times the volume. Since we know the volumes have that relationship, doing the opposite of the cross multiplying, the relationship with the densities show that the density of the crown is in fact less than the density of gold. So this was not good for the goldsmith. When Archimedes responded back to this with his demonstration, the king, as the story goes, was not happy that he was told that this was a crown of pure gold, and in fact it was not. Okay. The goldsmith, as the story goes, admitted that he did put a little bit of silver in, just a little bit, not a lot, sire, just, so yes, it is, it isn't pure gold, but it's mostly gold. Well, the story goes that the king said, Archimedes, I want you to look into that as well. How much of this crown is in fact diluted by the silver? And this is where the Eureka moment comes in. So Archimedes, the story goes, took some measurements. We have got some simple measurements here. We, of course, have no idea what the real measurements were, but we do know the density of gold and the density of silver in our unit system. I've thrown away all the decimal points, by the way, guys. I'm just rounding all this to whole numbers. We're not interested in the decimal points. We're interested in the ideas, right? So the density of gold is 19 grams per cubic centimeter. The density of silver is about half of that, 10. So let us say that the weight of the crown, which he can weigh, okay, that's a known number, 240 grams. And he certainly, by his Eureka moment, he can take the volume of the crown. Well, let's say that that's 16 cubic centimeters. Just picking some simple numbers. Let's define our terms again. Now let capital G be the weight of the gold that's in the crown, the amount of gold that's in the crown, and V sub G be the volume of the crown, which is gold. Let capital S be the weight of the silver that's in the crown, and let V sub S be the volume of the crown, which is silver. We'll take the goldsmith's word for it. He's not lying anymore. Maybe that he only debased it with just one other element, and he used another precious element. He used silver. Didn't want to insult the king completely by putting in something like iron or something like that. So we'll take him at his word that we only have two different elements to deal with. Well, Archimedes has two equations that the weights add up to 240, the volumes add up to 16, but the problem is he has four unknowns. He doesn't know G, he doesn't know S, he doesn't know V sub G, and he doesn't know V sub S. He's got four unknowns with only two equations, a problem. But no, he does in fact have two other equations. He knows the density of gold. He can take a piece of gold, weigh it, take its volume, and do the division. He can find the universal density of gold, and the same with silver. This gives him his four equations. And notice there we can now solve for the weight of gold in terms of density. Here's that formula again that we're seeing now over and over. A weight is equal to a density times a volume. We're using this idea over and over. Density is 19, the volume of the gold, we're calling V sub G. And we can write the weight of silver also as the density of silver 10 times its volume. Now we're in much better shape. Now we've taken that weight equation, it's still a weight equation, but we're writing it in terms of volume. We have the original volume equation, as physicists so famously say, and which makes mathematicians grind their teeth. The rest is just math, because we have a situation that we've been dealing with over these last two classes, over and over again. Two equations, two unknowns, the substitution method. And we can just go to town. I went ahead and solved for the volume of gold there in that second equation. I'm sorry, the volume of silver. I rewrite my first equation with that substitution. Instead of using V sub S, I use 16 minus V sub G. We clear away, we do some algebra, we divide both sides by 9, and we get the volume of gold. Volume of gold, about 8.9 cubic centimeters. Subtracting that from the 16, we're left with how much was in silver. Of course, the king is not interested in volumes, he's interested in weights. He wants to know what the weight is. Well, that's easy enough. Knowing the volume, knowing the density, the weight of gold is 19 times that volume, about 169 grams. The weight of the silver in the crown is 240 minus that number, which is 71. Okay. Archimedes can report that the gold is only 70% of the weight of the crown, silver being about 30%. We do not know what happened to the goldsmith. The story ends right here with Archimedes' full analysis of the makeup of the crown. Okay, what I'd like to do now, here's one of those scary slides. If you look at it all at once, what the heck is going on? What I'd like to do is do that exact slide that we just did, but purely algebraically, without any numbers at all. And see if the mathematics, just the mathematical equations that we derive, we're going to derive the same equations, there just won't be any numbers in there. All of the quantities will be algebraic variables. Can we discern something about the nature of the problem, the nature of the composition of the crown in terms of its gold and silver makeup, just by looking at the algebra? Can the algebra speak to us as a language to give us insights that we don't see so easily, which are kind of blurred by looking at the numbers? The specific numbers don't allow us to see the more general idea that's behind this analysis. Let's give that a try. We'll finish this, and then we will basically have finished this unit, and we can stop for questions. We start exactly the same. We have the weight equation. The gold plus the silver is the total weight of the crown. We have the volume equation. The two volumes add up to the volume of the crown. And we have our density equations. We do exactly the same substitution. We transform that equation into a volume equation. We have two volume equations. We do exactly the same substitution I did before. Put in that substitution. Clear away. And solve here. Here, I've chosen to solve for the volume of gold. Let's say it's the gold that's of interest to us, okay? All I've done here, guys, I've simply multiplied the density of silver through the bracket, collected like terms, and isolated the volume of gold. Okay, I just swept this underneath. I swept this thing. And so here's one numerator over the denominator. So that's the volume of gold. Kind of an intimidating equation, doesn't really say much to us right away. The density of gold minus the density of silver, well, that's okay down the denominator. That's reasonable. Certainly the density of gold is a larger number, so at least the denominator is a positive number. Density of gold minus the density of silver, that has some kind of an intuitive feel for us. The greater, how much more dense is gold than silver. That certainly should be a factor in what the volume of gold should be. But the numerator, what the heck is the numerator? It's the weight of the crown over this term ds times Vc. What is ds times Vc? Well, here we're looking again at a density times a volume. That's a weight. What is the density of silver times the entire volume of the crown? What is the density of silver times the entire volume of the crown? Isn't that exactly the weight of a pure silver crown? That is the weight of the crown if it were made in pure silver. Now the equation doesn't look so strange to us. Now this numerator over denominator is two different differences, but the differences have a symmetry to them. The numerator is the true weight of the crown minus the weight of a pure silver crown divided by the density of gold minus the density of silver. Kind of a nice symmetric looking relationship. Suppose there were no silver in the crown at all. Let's stress our volume of the gold formula. Suppose there was no silver at all in the crown. That would be equivalent to saying that the density of silver in our equations is 0. What happens? Well, take a look at our volume formula. Make d sub s 0 in both the numerator and the denominator. What are we left with? We're left with c in the numerator and just d sub g in the denominator. Well, what is that? Well, solve for c. C again is a density times a volume. Okay, it is a weight like c, so it's a weight is equal to a weight. But just as the density of silver times the volume of the crown is a pure silver crown, then the density of gold times the volume of the crown is a crown made of pure gold. And sure enough, if there was no silver in the crown, the volume of the crown would be a crown of pure gold. And finally, if you look at that kind of very intimidating weight formula, I just simply multiplied the density of gold times that complex fraction, just stuck it there in front. But again, if we make d sub s 0 in our weight formula, what happens to our terms? We're just left with this. We're left with gg times c over dg, which is nothing more than c. So what is the weight of the crown in gold? It is the weight of the crown. the crown is made of pure gold. We're not deriving so much new knowledge here, right? What we're doing here is we're saying that the algebraic equations, by looking at the extreme examples, holds up. We did not derive these equations with these extreme cases in mind, but yet when we apply these extreme cases into the equations, they hold up and they continue to give us information which is correct. It's a very interesting phenomenon that mathematics can do. And we can imagine if these equations are not so intuitive and we stress them by taking extreme examples of the variables, we may in fact derive something that would quite surprise us, as opposed to this, which I think fairly say does not surprise us. It does not surprise us that if we make the density of silver 0 in our equations, we should wind up with a crown of pure gold if our mathematical analysis is correct. That the volume equation should show that the volume is a volume of pure gold, as it does. Okay, questions about our buoyancy discussion? No questions.
Nothing in the chat, Peter.
Okay, thank you. I know I'm going through this stuff quickly. The algebra is not something that you really need to follow step by step. That's something you can do on your own in the presentation. You have the presentation yourself. You can very slowly, open up these different lines as they go, checking my algebra. It's all algebra that we know very well. Let's go to the second one. I don't know if we're going to have time for the third on the balancing equations, which is really the simplest of the three. I wanted to get through these two where I think the algebra is more interesting. Here we're going to use the speed of different waves to find a distance. If these two waves start from the same place at the same time, but they travel at different speeds, let's see how our algebraic analysis can allow us to calculate what the distance to that disturbance is. We start with a few facts. The speed of sound in air, written as feet per second, miles per hour, or meters per second. The speed in water, notice, is faster. It's much faster, actually. It's more than 4 times the speed in air. This is true because of the stiffness of the water is actually stiffer than air, and the wave can travel more quickly through a stiffer medium. And moving along the ground is stiffer still, and a ground vibration along the surface of the ground can be as much as 9 times the speed of the sound moving through the air. And this is what this difference in speed will allow us to calculate the distance. So here's our little scenario. We have an earthquake which bubbles up to the surface and creates a surface wave from the bottom of the epicenter, and it also, of course, creates a sound wave. The whole Earth is being turned upside down. So 2 waves are going towards the receiving station, but they will arrive at different times. There'll be a gap in the time, right? And that gap in time is what we're going to use. That measurement is what we're going to use. Knowing the speed of the waves will be able to allow us to calculate the distance from the disturbance. We're going to use a very simple situation of just a sound wave and a simple ground wave. The way this is really done is the waves actually move through the mantle of the Earth. They're called S waves and P waves, but they do have different speeds, but they're more complex, and they derive directly from the epicenter below. They don't move along the ground, but there is a ground wave, as you can see in this analysis. There is a surface wave. These waves are more complex. They, for example, are not always of a fixed velocity. Their velocity actually slows down a bit as they move through, whereas the surface wave is actually more of a constant velocity. So we're going to simplify things and just work with a surface wave and a sound wave. Okay, our idea is to do the analysis of the math. Okay, so we'll try to keep the physical situation as one that we can cope with. But the principle is the same. The principle that we're going to use of a difference in the 2 waves is what is applied in the real world by the geologists using the different speeds of the S waves and the P waves. So we want to define our terms. We want to use some algebra. We need to define our terms. Let the distance between let capital D be the distance between the epicenter up on the surface and the receiving station. We don't know that number. Let T sub A be the time that the sound in air travels between the 2 points. We don't know that number either. We don't know the time because we don't know when this thing started. We just know when the receiving station receives the sound waves. And let T sub G be the time that the vibrations along the ground are traveling between the 2 points. And these two times, of course, are not the same because the speed of the ground wave is so much faster. It hits the receiving station so much sooner and so T sub G is much shorter than T sub A. But we can measure very accurately the time delay. We can measure the receiving of these two signals and very accurately measure the time delay. And that's what the scientists use. They use the time delay of these two signals coming into the station as their fundamental measurement. If they know the speeds, right, of the S waves and the P waves, or as we're going to use the sound waves and the ground vibration waves. So, for example, if we had a receiving station in which the ground wave was received, not knowing this, but at 3 seconds after the earthquake started, and the sound wave in the air is received 5 seconds later, then that would be, the time delay. Because I emphasize, we don't know when the earthquake started. We're just sitting in the receiver station. We're not at the epicenter. Okay? We're in the receiving station, simply receiving two different signals coming at two different times. That's all we have in terms of that data. What we're going to use is the known speeds that these things move at in order to make our computation using our algebraic analysis. So this is what we know. We know T sub A minus T sub G, I'll use the numbers of my example, is equal to 5 seconds, let's say. Notice that T sub A is a bigger number than T sub G. The amount of time traveling through the air, the slower wave, is a bigger number than the time that the fast wave is moving from that same epicenter to us. And so this is a positive number. This would be the time delay. I also know that the distance is the velocity of sound times the amount of time that the sound has been traveling. It's equal to the velocity of the pressure wave times the time the pressure wave has been traveling. I don't know what D is. I don't know what T sub A is. I don't know what T sub G is, but I do know those mathematical relationships are true by definition. And by definition, the distance to the epicenter is how fast the sound wave is moving times how long it's been moving. It's equal to speed times time. And I do know one more thing. I do know that the pressure wave is 9 times faster than the sound wave. This I do know. Okay. So let me take that time equation and turn it into a distance over speed equation. Yes, distance is equal to speed times time. Solving for the time is equal to distance over speed. And so I have d over speed of sound minus d over the speed of the pressure wave is now equal to 5. I'm working towards a substitution, right? But v sub g is nothing more than 9v. And now I have one fractional equation, which we all know and love, just in terms of one unknown, just in terms of the two unknowns. Just in terms of the one unknown now, d, v is now a known number, right? V is the speed of sound. So I can multiply through by the common denominator, 9v, collect like terms, and solve for d. Very straightforward, okay? And I get a number, 1,912 meters. And this is the basic principle. The math is more complex using the P and S waves, but this is the basic principle involved of using two different speeds. Notice it's the time delay, from the time delay, which we only know a composite number of 5, since we know the time delay is from the difference of 2 times, I can write those 2 times in terms of distance and speed. One speed I know. I know the other speed in terms of the first speed. And so I'm able to use my algebra to isolate just the final unknown, the distance. Before I just mentioned a very important time delay in the recent history of physics. Do we have any questions about that little analysis that we did? Okay, here's an example. In 2015 was the first time that gravitational waves were detected, predicted by Einstein way back in I think 1916, 1917, when he predicted these waves. He thought they were much too weak to ever be detected, never to be detected in any kind of technology that he could think of. But in fact, they were detected by a wonderful device called the LIGO observatories, the Laser Interferometer Gravitational Wave Observatory. There were two at the time in 2015, one here in Livingston, Louisiana, and one here in Hanford, Washington, very far away. We will see why important. And what the observatory looks like is this. It's more than a 2-mile track going in 90-degree directions. And a laser beam is generated here at the station, and it's split in two. So it leaves this point, two different half waves starting exactly at the same place at the same time, because the wave is literally split by a fancy mirror. It's sent down this track of 4 kilometers, hits a mirror, and comes back in this direction and back. And there's a very sensitive device at that station which can tell whether those two signals are coming back exactly at the same time because they left the station at exactly the same time, or are they coming back at slightly different times? The detection process is not important to us. It's an interferometer process, wave fringes, interference fringes. Those details are not important to us. We just have to trust in the fact that the physicists have worked this out, that they can measure very, very exactly. Even the tiniest time delay on one of those arms will show up on their detector. And for most of the time, they turn this thing on, and the detector shows that there's no time delay at all. Okay, these distances have been measured out with the greatest precision, and the two laser beams hit those distant mirrors, come back, and verify that they're coming back at exactly the same time. Of course, if a truck were to rumble by, or if there was an earthquake in that area, and the whole thing would begin to shake, and would deform, that long tube would deform in some way, then the detection would show that no, all of a sudden those two arms are not of equal length. The detection would show up even with the minutest change in distance. That's why there are two. The reason why there are two set so far apart is we don't want to have any false signals. We don't want to have any minor disturbances in Livingston fooling us that in fact we actually detected a real change in the distance of true space, which is what a gravitational wave will do. It'll deform space so that the length measurement will no longer be the same in both those directions. By having two stations very, very far apart, then a rumbling truck on one of them is not going to be detected on the other. And the two signals that they get with a time delay should be exactly the same. And when the system was turned on, guys, in 2015, only after a few days, amazingly, this was discovered. A signal was discovered, the identical signal was discovered with a 9-millisecond time delay at that distance. The same detection of the interference fringes were changed in precisely the same ways, 9 milliseconds different time delay, where the Louisiana site saw the signal first. The nature of the signal and the physics of the situation allowed them to actually compute what was creating this disturbance, these two black holes of different solar masses. Quite an amazing amount of astrophysics involved in taking this crazy looking signal here and being able to analyze it to make such a deduction, quite marvelous. But the 9 millisecond time delay tells us two things. One, this is not a fluke. One, this is something that is happening in space across the entire continental United States, because it's happening so far away. And the time delay of that amount and the fact that it happened in Louisiana first tells us that the source where the astronomers should look for this phenomenon in the real world should be in the solar and in the southern sky. And there's even a kind of a basic direction that can be looked at, in kind of a cone direction can be looked at because of the nature of this particular time delay with those two positions. So time delays. Okay, we want to again go through the little bit of time we have left, some of the analysis of what we did with the numbers to see if the algebra can tell us something more than just the actual distance of the epicenter. But before I do that, do we have any questions so far? I really don't want to take any questions now on the whole LIGO story and the black hole. That really is a kind of aside just to show you the importance of time delays. There are other examples, but I'd rather stick with our algebra questions if we could. All right. So here's one of those scary slides again, because we're going to be working in pure algebra. There'll be no numbers here, but we'll see if the algebraic equations that we derive without the numbers can tell us something a little bit more than what the numbers are telling us. Because when looking at specific numbers, we may not see some of the generalities that are actually there in the relationships. So again, we'll define our terms. D is the same, B is the same, and T sub A and T sub G. We'll keep our variables the same, but here's our measured quantity, the time delay. The time that the wave of true sound is traveling through the air, and the time that the pressure wave is moving through the ground. We don't know those two numbers. We only know their difference. We can measure very, very accurately when they come in to us, like God knows where, how far away, God knows where, but we can measure very accurately the difference in time of when we detect them. And that's the secret of this whole thing, is that very accurate measurement of the time delay. And we also have the fact that by definition, the distance to this disturbance is V times D sub A, is Vg times D sub G. The distance is equal to the speed times the time. And let us say that we know the ratio of the speeds. We know what K is. We know how much faster the ground waves are than the sound. This is measured in the lab some other place, and this is information that we have, just as the meteorologists know all about P waves and S waves. So now we're going to go through exactly the same algebra as we did before, except we're not going to have 5. This is no longer 5. This is now, think of it as a known quantity. Okay? It's an algebraic quantity, but it's one of our knowns. It's D, which is unknown. Okay? That's what's unknown. Can we derive an equation for D? Well, yes, because I can do the same substitution. I can multiply through by the same common denominator. I can try to isolate D on one side and everything else on the other, and solve for D. Sweep that K minus 1 underneath, divide both sides of the equation by K minus 1, and get, again, an equation for D, which is not all that intuitive. I would agree. This does not jump out, oh yeah, well, look at that. That's clearly what D is. No, that's not the impression we get. But if we can analyze the algebra, can we look at that algebra? Can it tell us something? Can the mathematics tell us something? We see it is the distance is a component of 3 factors. There's this interesting factor of K over K minus 1, that ratio of the speeds of the two waves divided by itself minus 1. K, of course, is a number greater than 1. We're assuming that it's a faster wave. So what is this K minus 1 term? Interesting term that comes up here. There's the velocity of sound, which we know, and there's the time delay, which we have measured very accurately. So it's a very nice formula. It's a formula we can plug in immediately. right? We can program our devices to, as soon as we get the time delay, we can immediately calculate the distance to the epicenter. We have k over k minus 1 ready to go because we know what kind of waves we're dealing with, and we have the velocity of sound ready to go. So it's a nice formula, but does it tell us anything without the numbers? Well, look at that v times ta minus tg. What is that? Well, notice it's a distance. It's a velocity times a time. It's the time delay. It's nothing more than the distance that sound goes during the time delay, right? It's how far the sound travels during the time delay, okay? After we have received the first signal and we now have this delay, while the delay is going on, that's what this distance is. It's not the whole distance. It's only the distance of the time delay, not the total distance, not the total time that the sound has been traveling at. It's only the time delay. But look what we're multiplying it by. We're multiplying this distance, which comes up short, because it's not the full distance out to the beginning of the epicenter, but we're multiplying it by a number bigger than 1. And so somehow or other, they compensate each other, and multiplying k over k minus 1, that strange ratio, times just the distance that the sound travels during the delay, will in fact give us the entire distance. Very interesting formula. Let's look at it one more way. Let's multiply. Let's take that. We'll take our formula again. And now let's multiply the v through the bracket. Let's distribute the v through, okay? And now we have something else. What are we looking at now? We're looking at two different distances, aren't we? We're looking at v times a ta and the v times a tg. Two velocity times times terms. They are distances. They should be, because the whole thing is equal to some multiple of a distance. What is v times t sub a? What is the velocity of sound times the amount of time the sound has been traveling? The total time the sound has been traveling times the velocity of sound. Isn't that the distance? That's exactly the distance. And what is v times t sub g? It's also a distance. It's the velocity of sound times the time that the fast signal was traveling through the ground. Just a very short amount of time, just a piece of the amount of time that the sound was traveling, just the amount of time that the fast wave took to get to the station. What, can we say that in words? Yeah. It's equal to the distance that the sound travels during the time the ground vibration was traveling. So what is the distance? It can also be written as this strange ratio over the distance minus a little bit, I take away some of the distance, just as I have up above. But I've compensated it because I'm multiplying by a number bigger than 1, k times k minus 1. But here's the kicker, guys. If you look at the two descriptions in red, look at these two descriptions in red. One is a distance that the sound travels during the time delay. This is the distance that the sound travels while the ground vibration is traveling. That's the complement of the top distance. Those distances together add up. Those two times, I'm getting too excited. Those two times together add up to the total time that the sound in the air is traveling. They are the complements of each other. They are the two pieces of the duration of time that the air sound, the true sound, is traveling. We have written the distance in terms of those two pieces of the sound. One, the actual time delay, and the other just the front end, the part in which the fast wave is moving. Because once it reaches there, the sound wave is still in the back somewhere, and all we have left is the delay when finally this true sound wave finally hits the station. So we seem to have written algebraically the distances in two very interesting ways, using these two different complements to the distance broken up by the sound wave. And the missing component, what compensates for it, is the very same ratio, k over k minus 1. Okay, I want to turn this around one more time and give you one more heavy piece of algebra. Suppose we turn this whole problem around to an experiment, to a lab experiment, in which we use this formula that we derived to measure the speed of the ground waves. Let us go ahead and set up a lab process, everything controlled the way we want, so we can measure the speed of these waves as they go through different mediums. Like, for example, if we take a long tank of water, okay, and let the sound wave, when the splash hits, when the vibration is created, we get the sound wave, the disturbance going through the water, and the disturbance going through the air. Let us take a known distance, a known length of the tank of water, or the known tank of whatever material, gravel, whatever material we want to try to measure the sound of these waves going through these materials, a known distance, continue to use our sound waves as our baseline, knowing the speed of sound. And what we can go ahead and measure from our distance formula is therefore the one new unknown. Now the distance will be known in the formula. We'll be able to measure the speed of the wave in the other medium. And in fact, we really don't need to measure this. It's not really the speed that we're after in the sense. We're interested in k, because once we know k, then the speed that we'll derive, of course, is just that multiple, k times the speed of sound in air. So we're really after the measurement of k in that sense. So we have a measured time delay. We have a known distance. We have our tank of water measured of a length. We still have our formula that we have for the distances, where little v is known. The velocity of sound is a known number. It's v sub g, which is not known. V sub g we know is equal to k times v, so it's k, which is not known. Once k is known, v sub g is known. So we've set up a little experiment. We do exactly the same algebraic analysis. We take that time delay formula, our formulas in a difference of t's, and write them as a differences of distances over speeds. Again, this is a known number. We can go ahead and multiply through by the common denominator, just as we did. But now we're interested in k, right? As we had that practice in solving for different letters in our different equations. Now that really wasn't, it really wasn't just a simple exercise for no reason. We do this all the time in our analysis of the real world, depending upon what it is we're trying to isolate, what it is we're trying to study. Here we're trying to isolate k. After we multiply through the common denominator, we can get all the k terms on one side, d is left on the other, factor out the k, and we get kind of a forbidding formula, again, something which doesn't jump at us right away. But in fact, k is equal to the distance of our tank, the length of our tank, over this kind of big denominator, d minus this expression v times the time delay. Yeah, we've seen that before. V times the time delay. And so what is k? Yeah, we're getting used to reading these, right? It's d over d minus the distance that sound travels during the time delay. We know that distance is less than d. Okay, it's only part of the distance that the sound gets to travel. We're only looking at that distance there during the time delay. So that number is in fact less than d, and we do have the denominator. I'm sorry, it's a number that therefore d minus that thing is less than d. The denominator is in fact less than the numerator, all of d, and k is in fact greater than 1. How much is it greater than 1? Well, by that ratio of d over d minus the distance that sound travels during the time delay. Very interesting to see it that way. Does that make intuitive sense to us? If it does, terrific. If that formula makes intuitive sense to you, that the ratio of how much faster the pressure wave is equal to the length of the tank divided by the length of the tank minus the distance that the sound travels only during the delay. If that makes intuitive sense to you, I congratulate you. It doesn't make intuitive sense to me. I see the symmetry to it. I see it makes sense on one level, but I wouldn't exactly be able to put those ideas together and say that's exactly what the ratio of the speeds are. But this is what the algebra tells us. So maybe there's a way of looking at this in more detail, continuing to analyze this to see just really what is behind this. Okay. Let me take that formula for K and do one more little piece of magic with it. Let's divide everything through. Let's divide all the terms, numerator and denominator, by capital D, by the length of our tank. We'll get 1 up on top of the numerator, and we divide D by both pieces of the denominator. So D into D is 1, and we'll get the D, divided by that second term. I've written it conveniently as V over D times that time delay. The time delay, guys, is not in the denominator. So don't be confused by the lexicography of this thing here. Okay, it's V times T minus G over D. Okay, that TA minus TG is over 1. That's in the numerator. Okay, though it looks, if you look at it quickly, it looks like it's in the denominator. It is not. It is a fraction times the whole number time delay. Well, again, this formula doesn't tell us a lot either. It isn't much. It's got some ones in it. Maybe I've kind of put all the variable terms there, all the measured terms in one place, but still it doesn't speak to me too much. What is K? Well, it's in this form 1 over 1 minus capital X, this funny term. Capital X is V over D, that fraction, times the times delay. Can this tell us something? If we look at it in this algebraic form, there's something more that we can glean. With the few minutes that we have, let's see if we can finish this off. So we know V, D, T sub A. These are all our constants. K apparently only depends upon T sub G, right? T sub A is not changing, whatever it is, okay? The tank has a certain length. The speed of sound is a certain number. Therefore, T sub A is a certain number. It's the amount of time it takes the speed of sound to get through the length of that tank. Those numbers are not changing. What's changing K is T sub G, right? The amount of time the water sound, the vibration in the water is changing, or whatever material that we've got this vibration going through, whatever medium we have going through. So stick with me here, guys. The last piece, let's look at it. Let's stress this equation a little bit. Let's look at some examples that we really weren't thinking of when we derived this distance equation. Let's look what happens when T sub G gets smaller and smaller. That is, the wave that we're talking about is getting faster and faster and faster. And the amount of time it takes to get through the tank is getting shorter and shorter. As T sub G goes to 0, look what happens to X. Look what happens to X. As T sub G goes away, all we're left with is V times T sub A over D. But isn't that the very definition of D? Isn't V times T sub A the very definition of what the length of the tank is? So X simply goes to the number 1 as the time traveling of the pressure wave gets shorter and shorter. Well, as X goes to 1, look at what K is. K gets closer and closer to 1 over 1. So I'm sorry, as X goes to 1, our denominator goes to 0. As X goes to 1, 1 minus 1 gets closer and closer to 0. K gets larger and larger. So our velocity gets greater and greater. This again is not surprising, right? Obviously, as the amount of time for this pressure wave to get to the end gets shorter and shorter, yes, the speed must be getting faster and faster. But do we have an extreme example of this where the speed is virtually infinite? Yes, we have the situation of lightning and thunder, right? When we see the flash of lightning in the sky, we know that that is virtually instantaneous to anything that we can see of a cloud any miles away. It is virtually instantaneous. And how do we measure the distance? Remember, we learned this as a kid. Since the speed of sound is about 1,000 feet per second, if you go ahead and count from the lightning, 1001, 1002, 1003, and then you hear the thunder, that time delay, you can use the full time delay of the 3 seconds times the 1,000 feet per second. And you say, oh, the cloud is about 3,000 feet away. Okay? We learned that as kids. Well, let's see if the algebra can verify that. As the time becomes zero of the ground wave, okay, like the lightning, which is instantaneous, as we saw that k goes to infinity, what happens to k over k minus 1? Finally, we confront this k over k minus 1. What happens as k gets bigger and bigger and bigger? Well, it's going to infinity. That's weird. Like, no. Think about it as it gets bigger and bigger. What is 11 over 10? What is 101 over 100? What is 1,000,001 over 1,000,000? These fractions are getting closer and closer to 1. And therefore, what happens to our distance formula as k gets larger and larger? This becomes 1. This goes to 0. And all we're left with in our distance formula is just v times t sub a. Just what we learned as kids to measure the distance to the cloud. It's simply the speed of sound times the full time delay, because the time delay is virtually the full thing. And the last one, just indulge me, one more stress test. Suppose that there was no time delay at all. Suppose we had 2 signals coming with virtually the same speed, and they always came to the station at exactly the same time. We would lose all of our information, right? There will be nothing to hook onto. There will be no way to compute a distance using this kind of information because there is no time delay. They come to us together. What should happen to our distance formula? It should become meaningless. It should become useless because we've lost the very thing in our analysis which led us to the formula. Can the algebra show us that? Can the algebra show that if this is the case, the algebra will disintegrate right in front of our eyes? It will not give us the wrong answer. It will truly disintegrate in front of our eyes. So let's go through that analysis again. What happens as t sub g gets closer and closer to t sub a? Look what happens to x. Okay. If these two numbers are the same, we virtually get 0 here. So we get v over d times 0, which is a perfectly nice number. X becomes 0. That's no problem. What happens to k? As x becomes 0, k becomes 1 over 1. There's nothing wrong with 1. That's a nice number. And again, intuitively, we realize that therefore v sub g is equal to v. Yeah, that we knew. We know that the 2 signals have the same speed, but it's our distance formula that I'm curious about. What does the algebra tell us of our distance formula? Well, as t sub g goes to t sub a, as k goes to 1, look at our distance formula. And now we finally see the interest of k over k minus 1. When k gets closer and closer to 1, k minus 1 goes to 0. We get a 0 in the denominator. And our distance formula becomes 0 over 0, which is not the wrong answer. It is no answer at all. In algebra, this number has no meaning. It's telling us that our formula has become useless once the 2 speeds are the same. This is an incredible test of the algebraic analysis that we've done here, okay? By showing that it holds up even under the most extreme situations. Okay, I'm sorry to have held you over for more than 5 minutes. I apologize. I try not to do that. We didn't get to the third factor at all. I apologize for that, but I think I made my point of the power of algebra doing this kind of analysis. But I will, if there are any questions, do we have any questions before we go? If you're all kind of stunned and you don't know what to ask, I appreciate that as well.
Well, there's nothing in the chat, Peter. So
Okay, all I can encourage you guys, I know we've gone through this quickly, is the algebraic manipulations we're doing is stuff that you know. if you follow my presentation, if you go into slideshow mode and bring in the lines of the slide as they come in, if you can remember the presentation we just went through, the logic will come through and the algebra you will follow. And I think you'll see better on 1 second look. I know I'm always asking you to put in extra time. I know that. If you take one more look at this, you'll see what we've accomplished here. We've truly accomplished using our algebra as a language. It is telling us things that we did not see initially, even if they were in somehow or other intuitive. All right, guys. Have a good week. I'll see you next week.
Bye. Thanks, Peter.
Okay, bye-bye. I'm going to stop the recording.